Good day and welcome back to my pre-calculus class. Before this time, we have looked at the graphs of sine of angle, cosine of angle, and their variations. So right now we want to look at some other graphs. So we'll start with the graph of secant of an angle, say x. Recall that secant of an angle is related to cosine of an angle by being reciprocal of the other. Now, the first thing we'll notice is that we cannot divide by zero. So that means that the secant function will be undefined when cosine is zero. So, do we recall the points where cosine of angles is zero? We have, let's say, let us quickly revisit this 1, 0, 0, 1. Here is negative 1, 0, and here is 0, negative 1. So, meaning that cosine is 0 here. That is when our angle is pi over 2. It is also 0 here when angle is 3 pi over 2, and so on. Remember, this is just one rotation, can keep going that way. And you can guess that, well, if we keep going that way, it means when it comes back here, then it is 0 again. And it goes, when it comes back here, it is 0 again, and we can keep going that way. Okay, so what that means is that secant of angle will be having vertical asymptotes at those points, at those angles, because the cosine is never more than 1 in absolute value. That is, remember, cosine of angle, the range falls within -1 and 1. So if we take the absolute value of these, then we see cosine is never more than 1. That is the highest. It then means that the secant, being the reciprocal, will never be less than 1 in absolute value. Let me quickly show you that. Let us analyze that. Because we can write secant as, say, 1 divided by cosine of x. And we are saying that this item here is not going to be more than 1. It's never going to be more than 1. Remember, in analyzing something like this, if this quantity is, let's say, 0.5, then it means everything here will be 2. However, meaning it is more than 1. However, if our cosine, let's say our cosine is something like 2, then it means that the whole of this is 1/2, 0.5. If it is 4, so that is 1/4, right? 0.25, meaning, it's becoming smaller because the denominator is bigger. However, because we cannot go beyond 1, it then means that this whole guy will be greater than 1. I hope that makes sense. Okay, having said that, by observing the graph of cosine, we can actually draw the graph of secant. Let us see that. So I will just briefly do that here for us to see. So recall that from this 1, 0, 0, 1, -1, 0, and here 0, -1. So at pi over 2, cosine is 0. So let us look for pi over 2 here. Cosine is 0 there, cosine is 0 there, cosine is 0 here, cosine is 0 here, cosine is 0 here. And we say that At those points, secants will have vertical asymptotes. There will be vertical asymptotes for secant at those points. So I'm going to have something like this. Now, another property is that the secant is not going to go below 1. I proved that to us few seconds ago. I proved that to us. So let us see how we can use that idea to draw the graph of secant. So what we would do is we just have something like this. It's an asymptote, so the graph of secant behaves this way there. And here we have something like this, and here we have this, we have this, and at this point we have this, we have this, and um outside here we have, say, something like this, and yeah, something like this. Now, there is also an important property or feature for secant. So in this color, I'll say this is secant of x. Another property is that when the cosine is increasing, secant will be decreasing. Look at it. If I have y equals to 1 over x, inversely proportional, what that means is that if y is increasing, x is decreasing. And if x is increasing, y is decreasing, right? We have that property from when two items are, behaving in that way. The same thing happens here. Look at it. On this region, we can see that cosine, let me use this, cosine is decreasing here. So we see secant increasing in that region. And here, you will see cosine is decreasing. As we go this way, you see cosine still decreasing, and you see secants. Remember, we are always reading graph from the left. So the y values are getting increased, and it keeps going that way. Okay, let me show you one more. On this region, you can see cosine is increasing. Cosine is increasing as I go from left to right. However, you can see secant is decreasing on that region as I go from left to right. So that is just another property that helps us to know the behavior of secants in those blocks. Okay, having done that, these are some features of secants that I would like to talk about some of them. The stretching factor is absolute value of A here. When we graph secant, sine and cosine, we call A amplitude. We do not call A amplitude when we are drawing these other trig functions. Rather, we call them stretching factors. So A is a stretching factor. Remember what to stretch means? The period is 2 pi divided by b. If our b is 1 in this case, then the period will be 2 pi for secant. So the domain would be the entire negative infinity to positive infinity, except those points where cosine is 0. So we need to remove those points. And the range, starting from this, look at it. The range would be starting from whatever it is here, upward, right? and whatever it is here, downward. Okay, so we also say the vertical asymptotes occur, where they occur, where cosine of angle is 0. So that is where vertical asymptotes occur for secant. Like I said, there is no amplitude, and this function secant is an even function because cosine is an even function. Quickly, let us see that. Um, For an even function, we have shown before that f of negative x equals to f of x. Let us see with secant of negative x. So secant of negative x will be 1 divided by cosine of negative x. So which is 1 divided by, since cosine is an even function, so I can replace that by cosine of x. And this gives secant of x. And now we have shown that secant of negative x equals to secant of x, which is the definition of even function. And so we conclude that secant, secant is an even function. By now you should know how to prove that, how to show that for all the trig function or for any function in general. Okay, we can do the same thing for um, cosecant. Similarly, we can draw the graph of cosecant by observing the graph of sine. Just like what I did the other time, I'm not going to repeat a lot of things because it is the same thing. So again, if we go back to our unit circle, 1, 0, 0, 1, negative 1, 0, and 0, uh, negative 1. So we'll see that sine is 0 here. When the angle is 0, it is 0 when it is pi. So that is here, it is 0 and it is 0. So that is in one rotation between 0 and 2 pi. So it is 0 there. And beyond that, we also also, right, this is 0 and also 2 pi. When we are back, it is 0 there. So we have 0 there. And keeps going like that. 3 pi, negative 2 pi. And again, at those points, cosecant, we have vertical asymptotes at those points. We have vertical asymptotes. So the graph of cosecant, we have vertical asymptotes at those points. So we just do that. The same thing. So again, the same thing we said about the absolute value of sine, that is, we have 1 minus 1 less than equals to sine of x less than equals to 1. So sine, because it never goes beyond 1, then it turns out that cosecant will not be less than 1. So meaning that we will be having something like this for cosecant, just like we did for secant. Nothing fancy at all, nothing different. So the behavior this way. And again, because it is a reciprocal function, we have that when one is increasing, the other one is decreasing. And when the other one is decreasing, we have that the other will be increasing. So let's see. Here we can see this function is increasing here, and we can see cosecant is decreasing as we move from left to right. Okay, so that is the graph of cosecant. And briefly again, the features of cosecant. Again, we call A the stretching factor. The period is 2 pi divided by B. And in this case, if B is 1, then that is 2 pi. And we need to remove those points from the domain. Those points is where sign is 0, we need to remove that. And it turns out to be pi over B k. For example, let's say when B is 1. So that means at pi k, so you will see that is why when k is 0, I remove it. When k is 1, that is at pi, I remove it. When k is 2, that is 2 pi, I remove it. When k is 3, that is 3 pi, I remove it, and so on. When k is -1, that is negative pi, I remove it. When k is -2, that is -2 pi, I remove it, and so on. Okay, so the range, like I explained in the case of secant, we also have that it behaves like this. So from here upward and from here, oh no, downward. So yeah, that's okay. And now the asymptotes I just talked about, the points where sign is 0 that we need to remove. Um, cosecant is an odd function because sign is an odd function. You can prove that for it to be odd function, you want to show that f of -x should be equals to minus f of x. So you should pause this video and try to prove that. That is, you want to prove that cosecant of -x is going to lead to negative cosecant of x. You should pause this video to prove that. Just doing exactly what I did here, and in the end, you should be able to have this to show that cosecant is an odd function. Okay, let us move on to graph of tangents. So with this, we will begin with a graph of the tangent function by plotting points as we did for sine and cosine functions. So you recall that tangent is related to sine and cosine by this. That is, tangent of an angle is sine of an angle divided by the cosine. Now, the period of tangent is pi, not 2 pi, it is pi. And we'll see why. Because the graph repeats itself on intervals k pi or pi k, where k is a constant. To draw the graph of tangent, let us do exactly what we did with sine. Now, let me remind us some things. Again, we'll go back to unit circle. Go back to unit circle. We have, maybe that is too small. I will make it bigger. Okay, so we do have, let's say, 30, 45, 60. So here, you should know this in your head by now, root 3 over 2, comma 1 over 2. Here, root 2 over 2, comma root 2 over 2. And here is 1/2, comma root 3 over 2. And here is 0, comma 1, while here is 1, comma 0. Okay, now, I want to graph from -pi over 2 to pi over 2, right? I want to graph from here to here. Remember how I can get negative angles? Okay, so now let us just target, I just want to show you one of them, that's it. Say pi over 6. Pi over 6, which is 30, 30 degree or pi over 6. So tangent of pi over 6 is sine of pi over 6, which is 1/2, divided by cosine of pi over 6, which is root 3 over 2. And that is 1/2 times 2 over root 3. And that is 1 over root 3. I need to rationalize that as we have agreed to do in this class. So that is root 3 over 3. So I have it to be root 3 over 3. Okay, so negative pi over 6 is that, and we do the same thing. Look at this. Pi over 4 have the same thing. So if you divide that, that would be 1. So we have that, and so on. So we have all this. We have all this. Now, what we need to do now is to see the behavior of the function as tangent of angles, as our angle approaches negative pi over 2 or pi over 2. Let us see the behavior of tangents. So to do that, let me hmm, let me create a table here. Okay, let me create a table here to show you something. Okay, so I will just say x and call this tangent of x. And then I want to pick, so recall that pi over 3 in decimal should be pi over 3. Okay, so pi over 3 is something like 1.05 approximately 1.05. And I will also pick pi over 2 as we go to that. So that is around 1.57. So I want to check values as I get closer and closer to that 1.57. So to do that, let me pick something like 1.3, something like 1.5, getting closer to that 1.55, something like 1. Say 56. Can also pick 1.565. I don't want to get to 1.57, which is pi over 2. But let us see what is happening. Make sure your calculator is in radian when you are doing this. So when you find tangent of x, that is tangent of 1.3, you can only use calculator to do that. Even though we say we are not using calculator in this class, but we can only use calculator to do that. So 1.3, so that is around 3.6, 3.6. Okay, I will just put it to one decimal place. So if I do tangent of 1.5, so it jumps to something around 14.1. If I do 1.55, tangent of 1.55, I have, oh wow, I have something like 48 point, let's say 1.56, tangent of 1.56. In fact, I have 92.6, so to say. Let's do one more, 1.5. I don't want to pick 7. Let's say 561. I don't want to get there because I know I cannot get there because at that point, cosine will be 0 and I need to, you know, not use that value. I hope that makes sense. Tangent of x is sine of x divided by cosine of x. So this guy must not be 0. That is why I will not use either this guy or this guy. But I want to see the behavior of the graph. as we go closer and closer to that point. So tangent of 1.561. In fact, it got to 102. Let me do tangent of 1.566. That is 208. So let me say 6. So that is like 208.5. So now we can see that as we go closer and closer and closer to that 1.57, the tangent value is shooting up. It's becoming larger and larger and larger. So we know the behavior that it is going to infinity as we go closer and closer to that particular point. The same thing if you pick points here between negative 1.3 and negative 1.566. It's just going to be giving you, I can be smart with that because tangent is an odd function. So it's just going to be something like this. Something like this. So meaning it's becoming smaller and smaller and smaller. And then it turns out that we have, so we know the behavior as we go closer and closer. Remember, we are going to have, let me change the color here. We are going to have asymptotes at negative pi over 2. I hope that is clear because that is where cosine is 0. So we should have asymptotes there for tangents. It cannot cross that line. Okay, so let us plot our point. At negative pi over 3, it is negative root 3. There's a lot of decimals going on over there. But in the end, our graph turns out to behave this way. Um, okay, I can manage that. Okay, so it turns out to behave in that way on between negative pi over 2 and pi over 2. So you can see that the period is pi, that is pi over 2 minus minus pi over 2. So that is pi. So that is period to complete one rotation there because every other thing now is a repetition. So beyond that, we're just going to be having this similar graph. Okay. So what else can we say about graph of tangents? So the stretching factor is absolute value of A. Again, we don't call it amplitude, we call it stretching factor. And the period is pi over absolute value of B. In a case where B is 1, then the period is pi. The domain is all real numbers, except where x is pi over 2 plus pi over, let's say when B is 1, that would be pi over 2 plus pi k, right? Let me quickly show you that. So look at this at pi over 2. The next time cosine is going to be 0 will be when we have that, when we add this pi k to it. For example, if our b is 1, so we have pi over 2 plus pi k. So if k is 0, then it's at pi over 2. If k is 1, then that is pi over 2 plus pi, right? When k is 1 plus pi. So which is going to be something like this. and that is 3 pi over 2. So meaning the next one will be somewhere here. Somewhere here, where we have another asymptote, right? And we have the graph behaving exactly like what we have the other time, just like this, something like that. So, and so on. Okay, the range is negative infinity to positive infinity. You can see the range. You can see it's just negative infinity to positive infinity. And the asymptotes, we just talked about that. That's the point where cosine is 0. And tangent is an odd function. You remember? Tangents of negative x will be tangents of x. So you can prove that. In fact, you should pause this video to prove that just by saying tangent of negative x is, how can you rewrite this? Sine of negative x divided by cosine of negative x. Then move from there and make sure you are able to arrive at this. So sine is odd, tangent is odd, cosine is even, secant is even, right? Um, cosecant is odd. So the last thing here is the cotangent, which is again similar to what we have seen when we were dealing with cosecant and secant. So the last trig function we need to explore is cotangent. The cotangent is defined by the reciprocal identity, just like that. And again, the function is undefined when the tangent function is 0 because we cannot divide by 0. So again, the question is, when do we have tangent function being 0? Well, we have tangent function being 0 here, we have tangent function being 0 at pi, and so on. So those points becomes asymptotes for cotangent. So that is why we have asymptotes here. We have asymptote at 0. We have asymptotes at pi. At pi. Those are the points where tangent is 0. So, and because the range of tangent is from negative infinity to positive infinity. So it's just cotangent just take that as well. And the thing that helps us in this situation is when tangent is increasing, cotangent is decreasing. So that is the only thing we are left with, and we have the graph of cotangent of an angle this way. So this video, I just use it to introduce you to other trigonometric functions. I'm not going to go deeper on graphing their variations like we did with our sine and cosine. Because if there is a need for you to do that in the future, you can just revisit a text to, study that because it is the same thing or almost the same thing with what we have studied with sine and cosine. Okay, so this is where I'm going to be ending this particular video. And in my next video, I'll be teaching on inverse trigonometric functions. I don't want this video to be too long, so that I want to separate that. So I will be ending this one. Okay, I hope you enjoyed this brief video. I will see you in the next class.